Today is lecture 39, Math 141. We should wrap up max-min word problems, optimization problems. We have a few questions from WebAssign that we can look at least get them to the point where they're set up. And time permitting, we'll start Newton's method or Newton-Raphson method, which is a way of using the first derivative to approximate roots of an equation, or possibly to see where two functions are equal to each other. You can accomplish that as well. All right, so I'm looking at problem 9 on WebAssign. Find the area of the largest rectangle that can be inscribed in the ellipse below. All right, so the ellipse looks like this. We don't really know. I guess we could, for diagram purposes, say that A is larger than B, because that's kind of typical to the major axis, minor axis thing. So let's see if we can get a picture of this. So we would go out A units. On the x-axis to the ends of the, let's call it the major axis, B units. On the so-called minor axis, ellipse looks probably looks a little bit better than that actually, but we'll assume that that's our ellipse. So this is the point A0, negative A0, 0, negative B, and 0, B. So what do we want to do? The area of the largest rectangle that can be inscribed in the ellipse below. So there's a whole bunch of rectangles that could be inscribed in this thing. Of varying height and width. Here's one of them. I could make it longer, but it would be thinner, right? I could make it less wide, but it'd be a little bit fatter. But this could represent a rectangle, and we want to maximize the area. Okay, so what do we know about that point? And I think once we establish some facts about that point, we'll be able to come up with a length and a width for this rectangle, and then we'll get that area formula. I think once we get the area formula, everybody knows what to do. We're going to take the derivative, back up step, get it to be a function of a single variable, then take the derivative, set it equal to 0, or see where the derivative fails to exist. So this point would be over x and up y, but do we know anything? Let's say, to start with, we're going to go over x and up y. Now, if we kind of generated our area from there, what would our area function look like in terms of the x and the y that we have labeled? So the length would be 2x, and the width or height would be 2y. So we want to get rid of a variable. We do know the interrelationship of x and y. That is given by this. So if we want to keep the x's around and solve for y, or the other way around, what should we do?
Solve for one of the variables.
Okay. Does it matter? I mean, we're basically the same procedure. If we solved for y, keep that term here, move this term to the other side. What next if we're going to solve for y? Multiply both sides by b squared. And take the square root. Running out of room up there. So y would equal plus or minus, well, which one do we want? Let's just, it really shouldn't matter in a way, but we're dealing with area, so we want positive distances. So let's take y to be actually this point, which is positive. B squared minus, I'm going to call that b squared over a squared x squared. So if we've solved for y, what y is on this, and this is a point on the ellipse, in terms of x, we may not like the way it looks, but that's what y is equal to. So we should be able to throw that into the area formula. And instead of having an area formula of x and y, we'll have an area formula in terms of x only. So 4 times x times, instead of y, so we've got our function that we want to, in this case, maximize. Anything that we can do ahead of time that would make this the slightest bit easier to work with.
Take the square root of everything.
Okay, anything that we can take the square root of, which I multiplied both terms by b squared. I could have kind of left that out in front in factored form, and then I would have had the square root of b squared, which is b. So we can basically factor a b squared out of both of these. So for the square root of b squared is going to come out as b. We're going to have an x. And really, we can't take the square root of anything else. Nothing else is a factor. Is that correct? We don't have an a squared in the first term, nor do we have an x squared. We don't have, it's got to be in both terms in order to be factored out. All right, what would be next? I'm not going to do the whole problem all the way through, but let's get it to a point where I think you'll feel comfortable with it. What do we typically do once we have a function that's going to be maximized or minimized in it as of a single variable?
You said equal derivative.
Take the derivative, right, and then set it equal to 0. So the next step, and it's not trivial, is to take the derivative. Why is the derivative kind of testy here?
Because
It's got a pretty ugly square root in it, but it also has what? It's got a product, right? So here's the first term of the product, and here's the second term of the product. So we've got to use product rule, unfortunately. So once you use the product rule, you'll set that equal to 0. And also in this problem, is this going to be appropriate? Is the derivative ever going to fail to exist? No. So we'll just take the derivative and we'll set it equal to 0.
Is b just a constant?
B is a number, so that you can attach that to the 4 and just call that a coefficient. So first times the derivative of the second. That's got a little chain rule piece in it too, right? Because the derivative of the inside function has an x squared in it.
You have to do the product rule on the inside too.
No, that really ends up being a chain rule because so if you took the first times the derivative of the second, the first would be 4bx. What's the derivative of the second? 1/2 times the same quantity. what? To 1 degree less?
Mm-hmm.
Times the derivative of what's inside. What's the derivative of that?
Two.
That's a coefficient, right?
Negative two.
-2 over a squared times x. So there's the chain rule on the derivative of the function that's inside of the radical. So that's first. All of this is derivative of second. The second piece of it's not going to be bad. We do need to consider where the derivative is undefined. Because isn't that to the -1/2? Isn't that in the denominator? Right? So you would not only want to know where the first derivative is 0, but you'd also want to check out where the first derivative is undefined. So that's first times derivative of second. Then you'd go with second times derivative of first. What is the derivative of the first? 4b. So that's not going to be a tricky part to this. Yes?
Where it says chain rule, what
Yeah.
is that above the a squared?
That is the derivative of 1 minus 1 over a squared x squared. Is that. Derivative of the 1 is 0. 1 over a squared is a coefficient. And the derivative of x squared is 2x. So there's the 2 that's in the numerator. -2 over a squared times x.
Is there any way you can finish this problem?
Um,
This was like really
Yeah, I have no
confusing.
idea.
I got this far and I couldn't get it.
Let's see. Well, we'll probably have to pick and choose on one of these other two. I was going to hopefully get all 3 of them set up, but maybe we'll only be able to do one other. We can take it to a point where everybody feels a little more comfortable, because I sense that we're not there right now. Am I perceptive this morning or what? All right, so what do we have? First times derivative of second plus second times derivative of first equals 0. Just trying to think through that to see. I don't think it's going to be much different if we solved for x. Not enough to warrant even thinking about that anymore. Anything that we can knock out before we start trying to simplify? Well, half times 2, they knock out. We've got an x here times another x here, right? So we've got 4b. Actually, we've got a negative, right? There's a negative. So negative 4b over a squared. We've got this x times this x, so we've got x squared. And this goes to the denominator. So I'm going to go ahead and kind of put it where it belongs. Does that look like the first term? Got a 4b. We've got a -1. We've got division by a squared. So I brought all that out front. This x times this x is x squared. I threw that down to the denominator, and it's a square root. It's to the -1/2. Plus 4b So we want to know where that's 0. Any recommendations to make this a little easier looking? I guess we could take the negative term to the other side and make it positive. I think I want to do one thing before we do that.
Factor out 4B.
Okay, 4b can certainly be factored out. If we move this term to the other side, we could, in essence, divide both sides by 4b. I don't know. Let's just move it. I would probably multiply through by this radical here and here and here. But it's the same thing's going to happen. So let's just leave the positive term. Here, and we'll move this negative term to the other side, which makes it positive. So let's divide both sides by 4. Divide both sides by b. So those are gone. So let's put things in the numerator that belong there. X squared belongs there. That's it, right? Stuff in the denominator that belongs there. So this is over 1. Now we can cross multiply, and we have that ugly radical times itself, which any square root times itself, you're back to what's under the radical. And multiply these two, and you get x squared. So this radical times itself. Is that. Everything gets multiplied by a squared. Now we're a little better off, significantly better off, I think. Can we take the a squared and distribute it through here? Can do that now that it's not a radical, because we had the square root times itself. So a squared times 1 and a squared times 1 over a squared just is x squared. Gosh, we're getting there, right? So this is distributed. So we end up with 2x squared equals a squared. Feel a little better about taking it from this point as opposed to the other one. I hope. Okay, that's a much easier equation to solve than the one we had when we just had the first derivative and the product rule.
Leave that there for just 1 second.
So you'd solve for x. You'd also need to, gosh, that's, I don't know how appropriate that is.
We solve for x, not a.
Because you're trying to solve the first derivative equal to 0. First derivative in terms of x equal to 0. So you want x equals something. So what is x equal to in order to, in this case, maximize?
And then you have to plug that x value back in to get the y value.
Yes.
Into the original.
Into the original, because it is a point on the ellipse. So once you get what x is, you have the x coordinate of the point. Then you would need the y coordinate of the point. So you'd have an equation to solve for. What is y equal to? What did we say that it was?
Plus
B squared.
Yeah, times quantity 1 minus x squared over a squared.
That's what y was equal to, right, in terms of x? And there are other ways of getting there, too. Taking the x value and squaring it putting into the original equation. I'm avoiding saying this. What else do we need to do to validate that this is in fact a max?
Plug it into WebAssign and see if it's right.
Plug it into WebAssign and see if it's right. That might actually be a better response than what I was anticipating. What do we typically do when we think we have a max or min? Ooh, that sounds bad, doesn't it? So we would put it into the second derivative, right? Gosh, the first derivative was really bad. So the second derivative is going to be really, really bad. And we would expect, or we would hope, that when we plug it into the second derivative, if we want this to be a max, we want the second derivative to be negative, right? And if the second derivative is negative, that means it's concave down. And if it's concave down, then we have a max. Now, how does WebAssign find the area of the largest rectangle that can be inscribed in the ellipse? So we've got to go all the way back to the area function. Which area function in terms of x was this. Or I guess since we have an x and a y, we can go back to this. Right? Once we've established the x value and the y value, all we want is the area. So we can just take 4 times the x value times the y value, and we should be in business. Now, you shouldn't expect a number. You should expect an answer in terms of A's and B's, or maybe all A's, but possibly A's and B's. More than likely A's and B's. So if I could get by without validating, which I think you can in WebAssign, that in fact the second derivative is negative, therefore concave down, therefore it's a max. I don't think WebAssign actually demands that of you. Is that better to get it to that point? All right. Do you have a preference of the other two, which one we should look at?
Number 11.
All right, 11. A boat leaves a dock, and there are varieties of times here, so you're going to have different problems, but the movement, I think, within the problem is going to be the same. A boat leaves the dock at 2 p.m. and travels due south at a speed of 20 kilometers per hour. Another boat has been heading due east at 15 miles per hour, reaches the same dock at 3 o'clock p.m. At what time were the two boats closest together? All right, the other boat was heading due east, so it was over here, and it was going this direction. Heading due east at 15 kilometers per hour, reaches the same dock at 3 p.m. At what time were the two boats closest together? So I'm going to clutter this diagram and then redraw the diagram. All right, let's see if we can. So this one leaves the dock at 2 p.m. and travels south at 20 kilometers per hour. The other boat has been heading due east at 15 kilometers per hour and reaches that dock at 3 p.m. So this boat's moving along its way. Let's say it's right here, and the other boat left the dock and let's say is right here. So we're assuming a boat heading due south and a boat heading due east are at perpendicular paths to each other. So that's going to help the cause. So it might be right now that they are the closest together. Or this boat keeps plugging along at 15 kilometers per hour. This boat keeps going down here. It might, in fact, be that particular instant in time when they are closest together. Now, this problem actually kind of has an endpoint. Maybe this boat is out here, and this one just started. Maybe they're closest together when they're that far apart. So let's see if we can set this up, and then the endpoint would probably be kicked out like it was in the problem we did the other day. So we need to set up, let me get a new diagram here. So we've got this one. This line segment is getting longer. Is that correct? So from 2 o'clock on, this line segment's getting longer at the rate of 20 kilometers per hour. What about this other line segment? Because this boat was out here and it's heading toward the same dock. Isn't that line segment getting shorter? So what's the difference? Why would we want to establish if a line segment's getting longer or a line segment's getting shorter?
Negative.
Negative,
Positive.
okay? This one is lengthening, so its rate of change is positive. This line segment is getting shorter, therefore its rate of change is... So it's not like they're both starting from the dock and they're both heading out. That's another kind of problem, and we've actually done an example like that. But this time, this segment's getting shorter. This one is getting longer. So we'll call that positive 20 kilometers per hour, and the other one what? Negative 15 kilometers per hour. So we want to kind of freeze some particular instant in time. We don't know exactly when they will be closest together. But let's say it's when this boat is here and this one is here. Now, what do we know about the diagram to this point?
It's a right triangle.
Okay, we know it's a right triangle. So if we can get this described in terms of kind of an original length minus something based on how fast this boat is going, time, right? We can throw time in here, get it, 2 equations in terms of t. That's a single variable, so that'll work. How about this one in terms of t? Well, let's start at 2 o'clock in this problem. So if we start the clock, time 0 equals 2 o'clock. So starting from that point in time, if we go, t is in hours because we're in kilometers per hour. Let's say we go t hours. How far is this boat gone? Starting at 2 o'clock.
T times 20.
T times 20. Is that all right? Because it started here at 2 and it's going 20 kilometers per hour. So in t hours, it's gone 20 t kilometers. So that leg of the right triangle is 20t. All right, so we've got to backtrack with the other one. Another boat has been heading due east at 15 kilometers per hour, but we do know that it reaches the dock at 3 o'clock p.m. So where was it? Back over here. What was this distance? If we're going to start the clock at 2 o'clock p.m., how far away was that boat? 15 kilometers? So this line segment, when this one was just starting, was 15 kilometers long. Is that all right? Now that we've let the clock tick a little bit past our time 0, what's the length of this segment? It's not 15t. That's it was 15,
15 minus 15
and
times
now
t.
it's gone. That's exactly right. It's gone 15 kilometers per hour for t hours. So there's the length of this side. There's the length of this side. Is that enough to figure out the distance, what do we want, the minimum distance? Let me read it again. At what time were the boats closest together? So we want to minimize this distance. So what is that distance based on what we have thrown into this? Good. Pythagorean. There's one leg squared plus the other leg squared. And that is this distance. I don't want to use d because we're going to take the derivative of it. So let's just call it, I don't know, q. That's the quantity q squared, where this is q, the hypotenuse. Q would actually be the square root of that. Now, I think we've done this before on another problem. Didn't we minimize, although I think it was a maximum problem. We maximized the square root by maximizing what was under the square root, right? So we don't really want to work with this big, ugly square root. We want to work with what's under this. So let's call it something else, r. R is the quantity. That's what we want to make sure is as small as possible. We want to minimize the distance, therefore we need to minimize what's under the radical. Is that all right? Mm-hmm. So what would be the task from this point in the problem? Derivative, set it equal to 0. T would be in hours, and the starting time would be at 2 p.m., right? Something's not. Yeah, I guess we're okay. Because we have r in terms of t, so we'd be differentiating with respect to t. Okay, we're okay. So we would want to find r prime and set it equal to 0, and keep in mind that we started the clock at 2 p.m. Does that work? Does that help?
Why does it matter what time we started it?
Because of what we called this side. Well, actually, both sides. The fact that we're starting at 2 p.m., this one is just leaving, so that makes this easy. 20 kilometers per hour, t hours. So that's 20t. But the fact that this started at 2 p.m., we've also got to backtrack and figure out what the other one is, having started at 2 p.m. Because you can't start the clock differently for this boat than you can for this boat. We want to let them go the same time. So we have to start the clock the same for both of them. So this boat was out here at 15, right? I think we all, in fact, I think you said that it was out here 15. And then for every hour that goes by, it loses, this segment right here is getting shorter by 15t, where t is the hours passed since 2 p.m.
So once you set the derivative equal to 0, you're going to solve for t and plug your t into those two equations?
You're going to plug t, it's going to be a time. It's going to be a time in hours, and you'll just add it on. Or subtract it from, right, depending on what it is. If t is positive, which my guess is that it's going to be positive, you would add that amount of hours. So if t is, let's say, 1.333 repeating decimal, then that's 1 1/3 hours, right? So you'd add that on to 2 o'clock. So you'd have to put the decimal hours into minutes, probably.
But do we have to put that back under a square root?
Not unless it asked us what the closest distance was. It says at what time were the boats closest together. So we want a time. So this should be sufficient. And if they did ask another question, how far apart were they at the point in time they were closest to each other, then we would have to do what Casey just said. We'd have to throw it back into the distance function. All right, this is not due tomorrow, right?
No.
So let that be a jump start. If that's not going to get you to a place that solves your problem, we can revisit this tomorrow. Let's see if we can make a quick jump start on number 10 also. I don't know that we have sufficient time to get a good start with Newton's method anyway. And we've got time this week prior to the test to cover what we need to cover. All right, reading number 10. A fence 8 feet tall runs parallel to a tall building at a distance 4 feet from the building. All right, so there's the building. We're assuming that the building is perpendicular to the ground. 8 foot, so here's our fence that is 8 feet tall. That's not going to change in the problem. Parallel to a tall building, so that looks like it's parallel to the building at a distance of 4 feet from the building. What is the length of the shortest ladder that will reach from the ground over the fence to the wall of the building? Now, are there a lot of different ways that you could take a ladder, let's say, and put it, I'll redraw the diagram. It'd be nice to have something to actually draw it with. So let's say that we start the ladder right here. Is that possible? And we extend the ladder such that it just touches the top of the fence and it comes up here. That's possible, right? Would it also be possible to start the ladder here make it so that it just touches the top? I don't know. Did that seem to be a little bit longer? The one in green seems to be a little bit longer. So maybe there's actually a better one that optimizes this situation a little better to start it here, touches the top, and it comes up to here. I don't know what's actually going to work, but I know it's going to look something like that. So we just need to draw one, see what we can figure out about it. So there's the wall. There's the fence. So let's draw a ladder. Touches the top of the fence and comes up here. So we want to minimize, is that right? What is the length of the shortest ladder? We want to minimize the hypotenuse. Does that sound like what we want to do? Okay. Tell me some things that we know we have to get. Oh, we don't know this. In all likelihood, we're going to have to get the legs involved so that we can get leg squared plus leg squared equals hypotenuse squared. Thanks. Tell me anything that you think might get us going in this problem based on this diagram.
We know that the angle.
4 plus 6.
Okay, say that again, Nicole.
We know the angle, so we can do a trig function maybe.
Possibly trig. So you want to identify this angle? Is that what you're talking about?
Well, we know that that one's 90 degrees, so if we can figure out maybe another one, then we'd be able to do it.
All right, so let's give it a name here. right? So theta, now somebody else said something I think that was different from what Nicole said.
I said that that's going to be x under there, and the whole bottom is going to be 4 plus x. And you could do x to 8 as...
All right, okay, so hold on. She's saying, we don't know what this is. But that would be helpful to know, right? To where to start the ladder away from the base of the fence. If we knew that, then we probably could figure out the length of the ladder. All right, so you're saying this is x plus 4.
Then you could do like x over 8 is equal to 4 plus x over whatever you want to name the other.
Does that sound good?
Yeah.
I think that's worth a try. Use some similar triangles. And that's why when you said get the angle involved, that I thought that was going to be helpful, because isn't this angle theta in both of the triangles pictured? It's in the outside triangle, and it's also in this little triangle that has x and 8. So the fact that theta is the same, they both are right triangles, they are similar triangles. So if we establish relationships of sides that should be proportional, x is to 8 was Casey's suggestion. And what does that say then the matching sides are in the other?
X plus 4.
Want to give this a name?
Y.
Y temporarily. So x is to 8, so that looks like kind of the bottom segment is to the one that's perpendicular to it. So this bottom segment would be x plus 4 is to y. I think we're making progress here. Keep in mind, we're trying to minimize the length of the hypotenuse. Well, we've got x plus 4. I don't like the fact that we have y. You shouldn't like that. But don't we have a way now of getting rid of y? I think we do. So if we were to cross multiply y times x equals 8 times x plus 4, solve for y. Got some good progress going. We want now the length of the ladder. What's the length of the hypotenuse? Okay, this thing squared plus this thing squared, square root, right? So the ladder, let's call it L squared, is x plus 4 squared and we want the ladder, not the ladder squared. So the ladder and if we want to minimize a square root, how can we accomplish minimizing a square root without dealing with the square root? Just work with what's under the radical. You're going to make this as small as you can make it by making what's under the radical as small as possible. So give it another name. It's not the ladder anymore. It's a function that is under the square root, which kind of represents the ladder. Doesn't matter what you call it. So square everything out, distribute, group together like terms. Then you would want to take q prime and set it equal to 0.
How did we just get rid of the radical again?
how do you know that the square root of 2 is smaller than the square root of 11? How do you know that?
11's a bigger number.
Because 2 is a smaller number than 11, right? So can you make a quantity that is a square root, can you make it small by making the stuff that's under the square root small? That's what we're doing. So we're not going to mess with this outside square root in the derivative process. We're going to take the function that is under the square root. We're going to call it another name. We called it q. We're going to minimize q, which has the net effect of minimizing L itself. So multiply this out, group together like terms, take the derivative of that, and set it equal to 0. Now, it's a function in terms of x. What was x in our original diagram? X was the distance from the base of the ladder to the foot of the fence. But is that enough to figure out what this minimum ladder is going to be?
And you have to add 4.
Right. You would add 4 to that, which tells us this side. Isn't this going to be helpful once we get x? Right? Once we get x, we could add 4 to it. It gives us this side. Once we get x, we can add 4 to it, multiply it by 8, divide it by x itself. That gives us y. Once we know this side and this side, we can get the length of the ladder. So the question, what was the last statement?
What is the length of the shortest ladder that will reach from the ground over the fence?
Okay, what is the length of the shortest ladder? So we would figure out what L is at that point. All right, not what I thought would happen today, but that was useful. And we will begin with Newton's method tomorrow, or any other further questions from Max Min word problems.